Okay, standard model of matter, yeah? Here we go. Standard model of matter. Okay, there's different acronyms for it. There's SMM, Standard Model of Matter. Sometimes just SM on its own. Now in the HSC, if you're writing a long response question, you can write Standard Model of Matter first, once, and then in brackets after that, put SMM. And then from then on, you can write just SMM to save space. Save time as well. Okay, so what is it? Well, it's basically, it's a mathematical description of all the known particles in the universe, okay, all the forces and the particles. It's sort of like, the best way I can also define it, it's like the periodic table of particle physics. Okay, so chemistry's got a periodic table of all the known elements. Particle physics, we've got a thing called the Standard Model. It's a mathematical construct, okay? Mathematical construct which describes all the known fundamental particles and the forces which act between them. Okay, I think that's the best way to define it. And thankfully they've left out all the mathematical stuff in the syllabus because the maths is even crazy, right? It's heavily mathematical. Okay, so fundamental, if you remember what that meant. Do you remember what fundamental means? Anyone? Fundamental? Correct, yeah, can't be divided. So an electron, for example, is fundamental. Nothing else makes an electron. Correct. Okay, here we go. I'm just going to use SMM. Here's the standard model. Okay, here it is. So you've got two main categories of particles in the universe. You've got things called fermions, which are matter particles, and bosons, force particles. Bosons, fermions. Fermions, named in honor of the Italian physicist Enrico Fermi, the guy that made the first nuclear reactor. Boson, from Bose, the Indian physicist, can't pronounce his first name. That was very famous. No, sorry. Sorry, I can't pronounce it. I think Nayendra, I think? Nayendra. It's a long name. Oh, the fermions, okay. Now, fermions can be broken up into two subcategories. You got things called quarks. You don't remember what the other ones are? Leptons, yeah. Quarks, leptons. Okay, and there's 6 of each. 6 of each, quarks, leptons. Quarks. So who remembers the first? So there's up, down, correct. Yeah, keep going. Yes.
Top, left.
Well done. Yeah, good job. Up, down, charm, strange, top and bottom. 6 quarks. Up, down, strange, charm, top, bottom. Okay, these are called generations. This here. Okay, these two here, that's generation 1, that's generation 2, that's generation 3. Generation 1, generation 2, generation 3. As you go up by generation, the heavier the particles become. So the top quark is heavier than the charm quark and the up quark. That's what generation means. It's basically like a way to categorize them in terms of mass. Okay? Heavier, lighter.
So generation 3 is lighter, so it's heavier than generation 1.
Correct. And the particles that make up, the quarks that make up most of matter in the universe, they're in generation 1. Okay, these are too heavy. Heavy means unstable. If a particle is heavy, it's unstable. In the case,
Where would they exist?
they would exist in, let's say, cosmic ray showers. Okay, cosmic rays hitting the atmosphere, particle accelerators is all they can make these. So generation 1 make up most of the universe's matter. Okay, it makes sense because protons and neutrons, what type of quarks are they made of? Up and down, correct? Yep. Okay, they're also known as flavors. There's 6 flavors of quark. I don't know why they call them flavors. Okay, flavors, different types. All right, leptons, here we go. What are the 6 leptons? Here we go. Leptons? Yeah.
Electron, neutrino,
Yeah. Yeah, well done.
neutrino,
Yeah. Sorry. In order. Muon. Correct. Yep. Okay, this curly thing, curly symbol, that's new, Greek symbol. Okay, so there's 3 neutrinos associated with the leptons, electron, muon, and tau. Electron, muon, tau, and these are their associated neutrinos. Okay, they're like partners. They come with each of these 3 associated partners. Okay, wherever you find a muon, you find a muon neutrino. Whenever you find an electron neutrino. Okay, they're like partners. So they're the fermions in a nutshell. Is that familiar from many lessons ago? I think that was the first lesson in this topic. So it's good you still remember it. Well done. Bosons, here we go. Name me a boson. Force particle.
photon.
Thank you. Yeah, photon. Thank you. Go on. Yeah, W plus or minus. It could be plus or minus. Last one. Yes, Z for xeno. Z for Z particle. Okay, and these are neutral. Photons are neutral. Gluons are neutral. Z particles are neutral. It's only the W's that are charged, plus or minus. W particles, Z particle. Okay, what force does the photon carry? Thank you. Yep, electromagnetic force. Electromagnetic force. What force does the gluon carry? Gluon, what am I doing? Strong, yeah. Strong nuclear force. What about the W and Z particles? What's the opposite of strong? Yeah, weak, well done. Weak nuclear force. And there's one last special one, which is my bread and butter. Who knows it? There was one more missing piece of the puzzle up until 2012. One last particle. Higgs boson. Higgs boson. H for Higgs. What does that do? Anyone remember?
Mass.
Thank you. Yeah, it gives mass, so mass giver. So it gives mass to the fundamental particles. To fundamental particles. Yep. Talk about spin now. Spin. Okay, there's also a way to distinguish between fermions and bosons, something called spin. This is probably called spin. It's basically how it behaves in the magnetic field. Because let's say things like electrons, moving charges, they create a magnetic field. So it's like that token spinning, in the sense that it's creating a magnetic field. It has to be moving. an intrinsic quantum property of particles which dictates how they behave in a magnetic field. That's just a label that we give to particles, okay? How they behave in a magnetic field. Okay, will a gluon get affected by a magnetic field? No, it's not charged. Whereas an electron will. Let's suppose hypothetically a gluon. You've got an isolated gluon, hypothetically. Okay, it's not charged. Right?
So I have a question.
Yeah.
See how the Higgs field is composed of Higgs bosons,
Yes.
and the Higgs field allows the majority of the ferment of the amount of particles to have mass.
Correct.
Then how does Higgs bosons can give mass into them?
Question mark is still remaining to this day. No one knows. Good answer is perhaps string theory. So that's a possibility.
How can give mass?
Fermions, they've got something called half integer spin. What does that mean? So it can be a half, 3 halves, dot, 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 okay? E.g., an electron has a spin half. Okay, so it's a measurable number that comes out of experiments. I'm not going to explain it because it's not part of the syllabus, but it's just a measurable thing. Whereas bosons, they've got integer spin. Integer spin. So 0, 1, dot, dot, dot. E.g., Higgs has spin 0. Okay. Spin. Let's spin. Absolutely stunning how they come up with this. Fit together perfectly like a jigsaw puzzle. Right? The last piece, where is it? 2012. The first piece, 1897. Electron. Yeah. From 1897 up to 2012. Amazingly. And yeah, it all fits together. Sorry?
Is it complete?
It's complete. Complete except for gravity.
Gravity?
Yeah. It seems it's like driving in a car and you stop it on the side of the road, open up the front and you find there's no engine driving. Similar to that, sort of. How's it going on without an engine? But it turns out that you don't really need gravity at these scales. As far as we're concerned, so. Yeah, spin, that's what I talked about. It's just that's a good way to picture an electron. Okay, electrons that are moving create a magnetic field. Right? And if you put, yeah.
Is that the thing they recently discovered that even if they're very far away, the spin's like...
Yes, that's called entanglement. Yes. Yeah. Alright, let me get onto this. So quarks. Let's talk quarks, yeah? Quarks. Now quarks can only exist in pairs or triplets, or even more, actually. Quarks can only exist in pairs, triplets, dot, dot, dot. Okay, there are things called tetraquarks. You can make quarks that are in fours. Pentaquarks, they've made recent discoveries of those. Okay, but you can't have isolated quarks, apparently. So, particles that are made of quarks, they're called hadrons. Oh, they have quarks. Think of it that way. Have quarks, hadron. And there's two main types, baryons and mesons. Who remembers baryons? How many quarks? Three, yeah. 3 quarks. Mesons? 2, yeah. Most common baryons, what are they?
Proton, neutron.
Proton, neutron, yeah. That's right. Yeah, well done. Okay, so baryons look like this, like 3 quarks together. Q for quark. Mesons, they're made of a quark anti-quark pair. I should mention here, more technically speaking, quark anti-quark pair.
Are they the same quark or are they different types of, are they different quarks?
It's the counter to that quark. Let's say it's an up quark, it's an anti-up quark. Has to be-
How would they exist in the same space? Because if they,
No. Sorry. Let's say up quark. Let's say anti-down quark, for example. My bad. Yes. Right. So E.g., you've got the proton and neutron. Okay, they're the two important ones for the HSC. Mesons, you've got the pi meson, pi plus meson. You got the kaon as well. Just some examples.
Sabah, Jeannette, to the office, please. Sabah, Jeannette, to the office.
That's a great summary. That's based on the slides on Teams. That's a great summary. Great summary. Does that make sense then? It's not good enough. Does it make sense? Yes. Flavors, just another way of saying type, yeah? Different type. Bosons, I'll talk about this. Okay, and the Z actually stands for zero charge. That's why they call it Z. Right, zero, Z for zero. Okay, yeah, the Higgs is mentioned here. Discovered in 2012, July 4th, 2012. Never forget that date. Very important date in history. The history of science, in my opinion. And the reason why particles get mass. How was it detected? It was indirectly detected by particle decay. So Higgs was, because Higgs is very short-lived, it's got a lifetime of I think 1 yoctosecond, 10 to the minus something, 43, I think, yoctosecond. But it's a very short time, and it decays, and it creates other particles, and those particles, indication of the Higgs. So it's indirectly detected. Yeah, there was a lot of data analysis, a lot of statistics involved. Tons of it. Yeah, hypothetical, there's a proposed particle called the graviton for gravity. Hasn't been detected yet. Nothing there for that. Okay, it's a nice summary there as well. Other forces, what they interact with. Higgs interacts with everything. Yeah, Higgs field, that's a good picture to have. It's like a net, think of it like a net. Quarks interact with it, electrons interact with it, photons don't interact with it. So therefore they have no mass, right? And I'll leave this for part 2 of the standard model lesson. These are great. Right, so they get slowed down. As particles enter the Higgs field, they get slowed down, and scientists are able to agitate the Higgs field and create Higgs bosons. Okay, fields are made of bosons. So the electromagnetic field is made of photons. Higgs field is made of Higgs bosons. So they were able to agitate it, tap into it somehow at the right energy to detect the Higgs boson. Because remember, the Higgs is everywhere in space, everywhere.